The focus of this lecture will be on splitting fields, which we've already talked about a little bit. So I just want to start by recalling some things that we already know. The extension K of a field F is a splitting field for the polynomial f of x in f bracket x if f of x factors completely into linear factors in k bracket x, and f of x does not factor completely into linear factors over any proper subfield of k containing f. So we proved Theorem 25 in section 13.4, which said that for any field f and any polynomial little f of x in f bracket x, there exists an extension k of f that is the splitting field for f of x. So there exists some extension such that f of x factors as some constant times x minus theta 1 times x minus theta 2 times x minus theta n, where this theta 1 up through theta n are the roots of this polynomial f of x. And what was the idea? We showed very early in our study of fields that there is an extension of f in which this polynomial little f of x has a root. And the idea was to use induction on the degree of the polynomial. First, finding an extension where it had one root. In that extension, f of x factored as some linear factor times some polynomial of degree, at most one less than the degree of f of x. Okay, so I'll point out that now we have a little more language to talk about what's going on here. In this field K, this splitting field of this polynomial f of x, we have all of the roots of f of x, because f of x has to factor into a product of linear polynomials. So these roots, let's call them theta 1 up through theta n. Every element, every root of f of x has to be in this field K. And it's easy to see by the definition of a splitting field, because f of x does not factor completely into linear factors over any proper subfield of K containing f, that this splitting field K is actually equal to the field generated by theta 1 up through theta n over f. You just show containment each way. Yeah, so we have all of these roots that are contained in this splitting field. And once you have that description, you know where these roots live. They live in this extension of f. You can describe this splitting field as f adjoin theta 1 up through theta n. So the issue is that you just start with a polynomial, little f of x in f bracket x. You want to say, well, we'll just adjoin all of the roots. But all of the roots where? Right? Like, it's not so clear how to find some field that contains theta 1 up through theta n. That's what we had to do to prove that splitting fields existed. But there might be different fields that contain all of these, contain roots of little f of x. There might be different fields in which f of x factors completely into products of linear factors. So there might be different splitting fields. How are they all related to each other? This is what Corollary 28 in section 13.4 is going to tell us. It's the uniqueness of splitting fields up to isomorphism. It says, okay, there might be different splitting fields for the same polynomial f of x and f bracket x, but they're all isomorphic to each other. Okay, so we're not going to prove that now. We're going to prove that next time. So what are we going to do in this lecture that focuses on splitting fields? We're going to talk about some facts about degrees of splitting fields, and we're going to talk about several examples of splitting fields. So I'm going to pause and erase, and in this video, we'll focus on the first of these two topics. Let's prove proposition 26 in section 13.4 about the degree of a splitting field. So if f of x is a polynomial of degree n, then a splitting field for f of x has degree at most n factorial over f. Okay, and what is n factorial? It's n times n minus 1 times n minus 2 times 2 times 1. And what is the thing that we know is multiplicative? Extension degrees of fields. So the idea is going to be considering a splitting field over f as being given via a sequence of simple extensions. And this n factorial is going to be coming from giving a bound on the degree of each one of those field extensions. Okay, how does this work? So adjoining one root, this should say one root, theta 1 of f of x to f gives an extension f1 of f of degree at most n, right? This was how we started this whole discussion of fields, is we showed that there exists an extension of f in which little f of x has a root. What was it? It was given by f bracket x mod the ideal generated by the polynomial f of x, at least in the case that f was irreducible. So this has degree at most n. And in fact, we saw more. We saw that the degree was exactly n in the case that f of x was irreducible in f bracket x. Okay. So now let's look at this extension f1 of f in which little f of x has at least this one root, theta 1. It might have more roots, but it has at least this one root. In this f1 bracket x, how does little f of x factor? Well, it has a root, so it has this linear factor, x minus theta 1. So whatever it is, it's x minus theta 1 times g of x, where the degree of g of x is now n minus 1. So now same idea as before. If we adjoin another root of f of x, something that's not theta 1, but another root, so something that will be a root of g of x, okay, like you should think about what happens in the case where f of x has degree 1, where this statement is like obviously true, in the case where f of x is just a constant times a power of x minus theta 1 to the a constant times a power of x minus theta 1, so that the only root is theta 1. You can think about what happens in those cases. But in any other case, there's another root of f of x to adjoin. That's going to be a root of g of x. And now we're finding an extension of f1 in which this polynomial of degree at most n minus 1, sorry, this polynomial of degree n minus 1 has a root. And this gives an extension of f1, you could call it f2, of degree at most n minus 1. And when is that degree exactly n minus 1? When this polynomial g of x is irreducible in f1 bracket x. Okay, so continuing in this way, now we're going to look at how f of x factors in this extension in a f2 bracket x, and it's got at least this root x theta 1, and it's got another root theta 2. So it has these two linear factors. So it's the product of these linear factors times something of degree n minus 2. And you can just continue in this way until there are no more roots to adjoin. So using the multiplicativity of the degrees of field extensions, what is the degree of that field that you've gotten when you've adjoined each one of the roots? There's at most n of these roots. So at first you get an extension of degree at most n, then an extension of degree at most n minus 1, then at most n minus 2. So you get an upper bound for the degree of this splitting field as an extension of f of n times n minus 1 times n minus 2 times 2 times 1. So that's the end of the proof. And it's very natural to ask, can this be improved? Like, does this really happen where the splitting field has degree n factorial? And the answer is yes. I mean, we'll see some examples in this lecture of, let's say, for example, for a quadratic polynomial, you'll see splitting fields of degree 2. For cubic polynomials, we'll see an example where you have a splitting field of degree 6, which is 3 factorial. The answer is this cannot be improved in general, that for each n, most polynomials in Q bracket x of degree n have splitting fields of degree n factorial. That if you pick a generic polynomial, a random looking one, the degree of the splitting field will be n factorial. So there is some very precise statement to be made here, and we'll talk about this more later in the course. But for now, I just want to say that it's true that for most polynomials, you really do achieve equality here, that the degree of the splitting field is n factorial. But on the other hand, we're going to see all sorts of interesting examples where the degree of the splitting field is less than n factorial. So both of these things do happen for sure. All right, so I'm going to pause and erase and say a little bit more. Not only can we say that the degree of the splitting field is at most n factorial, but we can say something a little better, that it divides n factorial. And the idea is very similar. Let's say that theta 1 up through theta n are the roots of f of x in some splitting field, which we'll call k sub f. We've seen that k sub f is the field generated by these roots over f. And then we can think of this splitting field via a sequence of simple extensions. We've done this now several times where we take f to be f0, and we have f1, f2, up to fn, which is kf, where fi plus 1 is the field generated over fi by theta I plus 1. Okay, so we now see that the degree of the splitting field is the product of the degrees of fn over fn minus 1 times f2 over f1 times f1 over f0. And the argument that we just saw before is that this first extension has degree at most n. This next one has degree at most n minus 1, n minus 2, and so on. So something better is true. And this is a problem that was on the Algebra Comprehensive Exam in fall 2011. This is number 8, that not only is this degree at most n factorial, but it actually divides n factorial. And there's a hint given here, which is induction on the degree of f. So I'm not going to write down all of the details of the proof, but let's take the case where f of x is irreducible in f bracket x. Then what happens is, okay, you take this field f1 that you got by adjoining this first root theta 1, and this is an extension of degree n. And now, as we saw before, you have that f of x factors in f1 bracket x as x minus theta 1 times some polynomial g of x of degree n minus 1. So by induction, this polynomial g of x, we have a splitting field over this field f1, and the degree of that extension is at most n minus 1 factorial, but more than that, it divides n minus 1 factorial. So you have something that divides n minus 1 factorial times n, and that definitely divides n factorial. Okay, well, in the case that f of x is not irreducible in f bracket x, you have to think a little bit about the details, but I will leave that to you. So I want to end this video just by giving one more definition that I'm not going to use so much in the short term, but is going to be important later on in the course, that if k is an algebraic extension of f, that is the splitting field over f for a collection of polynomials. So far we've talked about the splitting field for one polynomial, but you can make the analogous definition for a collection of polynomials. So it'll be the smallest extension of f in which all of those polynomials factor completely into products of linear polynomials. So they don't factor that way. They don't all factor that way over any proper subfield. Then this field k is called a normal extension of f. Okay, so we have all the extensions of f, all the algebraic extensions of f. Some of them are splitting fields for collections of polynomials, and some of them are not. So whether or not an algebraic extension is a normal extension will be an interesting property for us to look into further. So in the next video, we'll see some examples of splitting fields.